So in any case, when you have questions, write it down in the chat or raise your hand, and we'll try to answer these questions as well as questions here in the room. So as Lionel pointed out, this is the first workshop in a series of 5. So we are starting here in Jena, and it's fitting into the topic of this exchange program that we established, FunGlass. So we want to have fun with glass and structuring. So we choose for the topic here for the first workshop, ultra-short pulse laser processing of glass. And we actually are very happy to have speakers from various fields, starting from laser development and then going towards processing of glass with ultra-short laser pulses. And with this, I'll just come to the first speaker. It's Arno Klenke from the Helmholtz Institute Jena and Institute of Applied Physics in Jena. Arno received his PhD a couple of years ago on coherent beam combining for ultra-short laser pulses, and since then is driving this field and doing performance scaling. And yeah, I guess he will report on the latest results in this direction. So slideshow. Okay, so this meeting will be streamed. That's good. Okay, stage is yours.
What? No, apparently not. Yeah, so thank you very much for the kind introduction. As was already said, my name is Arno Klenke. I work at the Helmholtz Institute Jena and the Institute of Applied Physics in Jena in the group of Professor Jens Limpert. In the next few minutes, I would like to show you some of the progress we have made, some of the recent development in using optical fibers for the amplification of femtosecond pulses. And I'll just start here with the, let's say, basic working principle of a fiber. What you can see here is this standard picture of a fiber. So you have in green this signal core that is embedded in a cladding outside. And in the simplest way, this green core basically just has a bit higher refractive index than the surrounding material. And that basically gives you a waveguide for your signal, shown here in yellow, where the signal can be guided. And if you now add some active ions to this green area, to the core, and add some pump light that can be guided in the core itself, but also in this, what we call the pump core, the fiber cladding, here shown in this purple color here, you can then actually amplify light that you have added into the fiber. And there are different materials you can insert into your core, different active ions, terbium, for example, erbium, known from telecommunication, or even thulium. I will talk about that a bit later. And most of our developments have been so far based on ytterbium as the material of choice. And there are a couple of reasons for that. So ytterbium has a high quantum efficiency. It has a low quantum defect. So you can see it on the left side in the scheme. You pump at 976 nanometer and emit at a bit more than 1 micron, so a very low quantum defect. And this basically makes this a very efficient material for amplification of light. It has also a very simple energy level diagram, so not so too many different cross-relaxation relations. And finally, very important, for 976 nanometers, there's an abundance of high-power pump diodes available, normally based on a semiconductor technology up to multiple kilowatts. You can just buy that commercially. And this has been very successful, this fiber laser technology. So when it comes to average power, this is the development, the record values of such systems. In blue, shown the dots in continuous wave operation, or in red for ultra-short amplification. And you can see this goes up to a few kilowatts of average power. And you have a very nice, this is a logarithmic scale, so very nice exponential development over, let's say, 2 decades. Yeah? However, you can also see, so last point is about at 1 kilowatt for pulse operation, about 10 kilowatts for continuous wave. The reason is the so-called mode instability effect that was discovered at around this point, 2010. And what basically happens in every fiber at a certain point, your nice output beam due to the waveguide is converted into this temporal fluctuating overlap of multiple beams shown here in this video. And it took some time to understand this effect. It has now basically understood, and actually work is going on to have passive or active mitigation mechanisms so that we can increase the power even more in the future. But I will later on in my talk also show you another way how you can build even more powerful fiber laser systems as shown here. So this was just related to average power, but we mostly work with ultra-short pulses. And if you do that, then due to the small confinement in your waveguide, so this waveguide is, let's say, has a diameter of a couple of microns up to multiple 10 microns. Due to a small confinement, you have quite high intensities if you go to short pulses. So there are a huge number of nonlinear effects that can happen that are cell phase modulation, Raman scattering, four-wave mixing, and at a certain point, there's even this self-focusing limit, which is not related to the intensity, but to the peak power. So even if you make your waveguide larger, this doesn't help you. At about 4 megawatts, you will see self-focusing and finally destruction of the fiber. And while most of these effects also have in certain, for certain ways, they are very useful to use them. If you just want to amplify ultra-short pulses, you normally try to avoid all these effects, of course. And the technology that actually makes fibers, I would say, usable for amplification of short pulses is the so-called pulse amplification concept. And you might know that Gérard Moreau, the paper is also given here at the bottom, received a Nobel Prize for physics a couple of years ago for this invention. So what you basically do is, on the left side, if you have a short pulse, this is shown here with this rainbow color, that means you have, if you have a short pulse, you also have a certain spectrum of different wavelength components. And when they are, if you have a short pulse, if they're compressed, basically all these spectral components arrive at the same time. And what you can now do is to add a stretcher, which is basically a dispersive media, often built on diffraction gratings, which introduces a chirp or dispersion to your pulse. And this basically means that you stretch the pulse in time. And this reduces your peak intensity and peak power. Then you can amplify it in your amplifier. And afterwards, you can recompress this. And in our systems, we regularly stretch the pulses more tthan 4 magnitudes from femtosecond up to the nanosecond regime, and can thus also gain 4 magnitudes about of power or energy per pulse. So this is the first way to do it, to make this usable for ultra-short pulses. The other possibility you have is to increase the diameter of your waveguide. So in the top picture on the left side, you see such a standard, I would say, telecom fiber with this very small dot in the center. This is your core of a few microns. And using different technology, and I will talk about this later, we have managed to increase the diameter of this fiber up to the right side, up to multiple 10 micrometers. And this larger diameter has two advantages. It, of course, reduces the intensity again, so you can go to higher pulse energies. And also it increases the absorption because you have more area, you have more active material. And so the length you need for your amplifier can also be reduced, which also reduces the effect of nonlinear effects. And so when you go to higher pulse energies for your fibers, you regularly go from this kind of standard flexible fibers that are quite long, that you see on the left side in the sketch, to such what we call rod-type fibers. So these are not bendable anymore and have a thickness of about 1 or 2 millimeters and a length of about 1 meter. Now the challenge you have just increasing your waveguide is normally not going to help you with your diameter, because the issue is if you just make your waveguide larger, what happens is that the so-called V parameter that you see at the bottom also grows. This is V, this is dependent on A, this is the diameter of your fiber core. And when this parameter grows, it means you add additional modes to your fiber. This reduces basically your output beam quality. This is normally not what you want to have. So the only choice you have is to reduce this factor on the right side. So the wavelength is fixed, you cannot do anything. But then A, you can reduce it by making basically this step index step from your core to your cladding smaller. But this is also possible up to a certain degree. So you are stuck with about fibers, let's say 15 micrometer of diameter that work in this single mode regime that you want to have. And now to overcome this, a lot of groups around the world have worked on what we call microstructured fibers. These are just some examples that you can come up with. And basically the idea is you want to have single mode operation at the end, but a larger core diameter. And as you can see, there are a lot of different possibilities. I will just briefly point out two of those. The first one, this is the LPF, large pitch fiber design, because the guiding mechanism, I will talk about the next slide, is through these air holes, and the pitch between those air holes is quite large compared to the other fibers. And the other one is the called DMF rod from NKT Photonics. It's a commercial product, and both can provide, let's say, mode field diameters of over 50 times the wavelength. So at 1 micron, over 15 microns, and you can get stable single mode operation up to, let's say, a bit more than 100 watts. And if you use CPA, you can get, let's say, a couple of 100 microjoules of pulse energies, which is already a useful system for a lot of application. I just briefly want to talk a bit about how this fiber even works, right? So this is not this, the working principle is not this simple index step, but it uses what we call delocalization. Yeah, you can see it in this sketch here, or on the left side, the fiber itself, yeah, with these air holes. On the right side, you can basically calculate the modes that can be put into the fiber, yeah, the fiber guides. And here you can see the following point. If you start with an, let's say, Gaussian beam at the input of your fiber, the chance is a lot higher that you will excite one of those modes on the modes on the left side, also the fundamental mode of the fiber, and not these higher order modes because they are quite outside of the central region. Yeah, so this is already this favored excitation. And then what you see, these numbers at the bottom are basically the overlap of these different modes with the active medium. What you can see on the bottom right, we have this green area, this ytterbium doped area. And of course, these modes that are very outside of this cores have a lower overlap, so are not amplified that much. So that means that even if you start with a mixture of these modes, at the end, your fundamental mode basically wins during the amplification process. You get in regularly about 30 times higher amplification than for the next higher order mode. So even if you put that into your fiber, at the end you get a nice output beam. This is a fiber type that we call effectively single mode. So it's not strictly single mode, it can guide different modes, but at the end your fundamental mode will win. Yeah? So this is was the standard fiber that we normally use in our system. And now I want to go to a few different topics. And the first development that has happened a bit over the last years, I would say, is to go to different wavelengths. And here, especially this region from about 1.5 micrometer to 3 micrometer is very interesting to build lasers in this wavelength region. One of the reasons is spectroscopy, because if you start from this wavelength region, you can easily convert these pulses to different wavelength regimes to a few microns. And in those wavelength regime, you have a lot of different, interesting, this is very interesting wavelengths for spectroscopy that you can see on top right. It's also possible here for certain materials for processing. You can see there's a picture of from IPG Photonics there. And also, especially in our group, we use this for strong field physics. So we often use these laser systems as drivers for so-called high harmonic generation, where we basically convert this light from normally 1 micrometer down to wavelengths of just a few nanometers, so soft X-ray regime. And if you want to go to very short wavelengths in the so-called water window, you need to start with the longer wavelengths. It's difficult to get there with just from 1 micron. It's easier if you start from a higher wavelength. Yeah? And that's why these kind of systems operating in this wavelength regime are very important to work on that. And one material that you can use is thulium, as I've shown you already on the first slide. The nice thing about thulium is it has a broad amplification bandwidth. You cannot build systems that amplify or output less than 100 femtoseconds of pulse duration. You have high power laser diodes, normally at 793 nanometers, quite widely available. And you can now combine this material with the technology we have developed before. So for example, this is a picture of a thulium large pitch fiber. So it's the same basic design, just your core is doped here with thulium. And you can see you can go to quite large diameters also due to the larger wavelengths of thulium. One issue you have if you work at 2 micron is the absorption in water vapor. And you might think, okay, but I'm not operating here near water, but even the water in the air, water vapor is enough to cause issues. So in black, you can see here these the transmission and the absorption here at different wavelengths regimes shown here. And you can see if you work at 1 micron, there's no issue. But if you go to 2 micron, especially where thulium emits, this is this red curve here, you are directly in this region of this water absorption. And what happens if you propagate a high average power beam through air, just through air, is can be seen here. You degrade your pulse in time, and you have what we call thermal blooming. So your nice beam gets into this kind of ring structure due to absorption in air, which increases the temperature in air, and this leads to this basic thermal lensing. Yeah, just by propagating through air. So if you want to operate these systems, you need to use a quite dry atmosphere or even vacuum. Despite that, we have been quite successful, I think, over the last years to basically follow the progress of ytterbium now with thulium and have now systems that work at high average powers up to 1 kilowatt, ultra-short pulses, but also these systems based on these large pitch fibers that can also emit ultra-short pulses with a few hundred microjoules of pulse energy. And today, I would say the performance is very comparable to ytterbium already. Now, in the basically last part of the talk, I want to talk about the topic I'm mostly working on personally. This is the so-called Coulomb combination process. And as you have seen before in one of the slides, so average power, there are limitations at a certain point. There are also limitations when it comes to pulse energy. You cannot just build larger stretchers to make your pulse larger. The diameter is also at a certain point difficult to scale. So what you do is parallelization. So instead of a single amplifier, you can use multiple amplifiers as shown here in parallel, and then you combine basically the output coherently. And to do that, you basically, the easiest way is on left side to start with a single input pulse, split this up into these multiple channels, then combine it again. And if you set the phases correctly, you can scale your average power and pulse energy by a factor of n, meaning the number of channels you have. And these are just some of the recent performance results. So we built a system with based on flexible step index fibers. This is really optimized for the highest average power with 12 channels, and we achieved over 10 kilowatts of average power. Also a very high combination efficiency of these different channels. And also at this point, your overall wall plug efficiency, so the electrical power you need to operate this, becomes quite important. And we achieved here over 20% for the whole system. Now, if we start from these large pitch fibers with larger core diameters, we can also have a system here with 16 channels running at a kilowatt, 10 millijoules of pulse energy, 120 femtosecond pulses, also high combination efficiency. This is also a system we basically use every day in our lab. But the question is, of course, at this point, how far can we go? How many channels can we combine? And theoretically, quite a lot. So on the right side, the combination efficiency, meaning the power you get out of these systems over the total power of all the amplifiers, is shown. And maybe contrary to what you expect, this total efficiency does not drop with the number of channels, but follows some of these curves that you can see here. Yeah? And we are more operating on this blue curve. So even if you had like 100 channels or 1,000 channels, at least theoretically, you should be able to build a system with high efficiency. However, we do not want to do it like this, because the issue is, if you look into a picture of this main amplifier here, this was this 10 kilowatt system. You can see 12 amplifiers next to each other. They are flexible fibers here. You can see the pump cables in yellow. And you also can see what the issue is, that the system gets very complex if you have so many channels. Yeah? And it's not just the amplifier. You also need, on the right side there schematically shown, you need to split up this input, what you see in red, these input beams into these multiple channels. You need to combine it. And even though the system was could automatically align itself at a certain point, you do not want to build such a system with 100 channels or even 1,000 channels. And so the latest development in our group is integrated components. So basically go back from using multiple fibers to just one fiber. But as you can see on the right side in the sketch, with a lot of single cores in just one single fiber. And you have a shared cladding, shown here in red. So you just need a single pump diode. You can also have to integrate all your other components for beam splitters. So instead of just splitting a beam always in two beams and then at the end combine it, we have developed such compact beam splitters and combiners. And also your phase stabilization system also needs to be integrated a bit more. And if you do all of this, basically you can build a system where the number of discrete components is, let's say, decoupled from the number of amplification channels you have. And the most important part, of course, is the fiber itself. How do you create such a fiber with a lot of single core? What's the production process? And we worked here with our colleagues from the Fraunhofer Institute on that, and I think came up with a very efficient process. So we start here with a preform shown here at the bottom. This is a fused silica, and there's another ring embedded fluoride doped. Yeah, has a bit different refractive index, and this is basically guiding of your pump light. Yeah, and what you then basically do is you drill holes into this structure. Yeah, you do deep hole drilling. This is possible with certain companies can do that. Drill these holes in, and then you have basically a preform that's on the right side shown here. You can stretch it out a bit, and at the end have this preform. You can see it on the right side with holes that have about a diameter of about 600 microns. And then you use active material. This has also been produced here at the Fraunhofer Institute. Shown here on the left side, you can see this is terbium doped material. You can see the step in the index step compared to the surrounding. Yeah, so it's a bit higher than surrounding. You can create those rods and put it into all these holes, and then you draw out the fiber. Yeah, and this gives you at the end a working fiber. And we, in the first step, we produced such a fiber. So this is also a rod type fiber. It's not a flexible fiber, so about 1 meter length. You can see a microsource picture on the left side with all these different 16 cores in it, and this ring for the pump guiding. And you can also see you get 16 very nice output beams out of this fiber. And we managed to, with all the other components, build up a complete laser system operating up to 500 watts of average power. Has also quite nice combination efficiency and also excellent output beam quality, as you can see also in the sketch. So this technology, we started a few years ago. We are also now getting to this point where this technology is quite competitive with the systems which have a lot of discrete amplifiers. Huh? And of course, we are working on scaling this even further. Now, the last, basically on this last slide, we have also been working on not going to higher average power, but actually, at a certain point, we also want to increase your pulse and our pulse energy quite a lot. And what we used one of those fibers which have larger core diameters. These are not single mode. They cannot be really used for femtosecond amplification and Cohen combination, but you can test energy extraction with this. Yeah, and we achieved here up to, let's say, close to 40 millijoule of total pulse energy, which is, I think, so far not has not been demonstrated from any fiber, at least not from a single fiber. And we think we can even go higher. And what we also tried at this point is using so-called tapers of this fiber. Yeah. So on the bottom left, you can see if you just take this fiber with 50 micrometer cores and try to excite here the different modes, you can see at the output all modes look different because this fiber, every core guides quite a number of modes, and at the end you get basically an overlap with a certain fraction in these different modes. Yeah, so every mode looks different. And if you add a taper that you can see on the top right side, so basically you make the fiber a bit smaller. Yeah, in a small piece at the beginning of your fiber, this goes down from 50 to about 20 microns. If you get better excitation at the beginning, and you get a lot nicer mode output profile here on the bottom right. And you can also see its m² value increases a lot. So this is also a technology we want to explore further here also for multi-core fiber to use these taper technologies. Maybe we can even get to a point where these beams have good enough quality to actually do a Cohen combination with them. which finally brings me to a summary. So what I've shown you is, so ytterbium-based fiber laser systems emitting ultra-short pulses can now provide, let's say, up to a kilowatt average power with this kind of CPA and core diameter scaling, with such microstructures fibers. You can go to higher pulse energies, up to multiple hundred microjoules, I would say. We have opened up new possibilities in application with thulium-based sources, also incorporating these advanced fiber structure at 2 micron. And finally, coherent beam combination gives you basically the road to even further scaling opportunities, first with multiple discrete amplifiers, and now with this multi-core fibers. You can see here this nice 4x4 fiber. And we are now working, this is the first picture of a 7x7. This was that we just discussed recently a few weeks ago. We are now running the first test on it. So you can see with this kind of technology, you can do a massive scaling of your cores, and then a massive scaling also, hopefully, of performance in a very compact way with these fiber-based sources. And with this, I would like to thank you for your attention.
Yeah, thanks very much, Arno, for taking us through this journey of the development of ultra-short pulse laser systems. Very impressive. Other questions? So maybe I'll start with one concerning the multi-core fiber. Yeah. What is the homogeneity of that one? And if you have different power levels in different cores, what is then the limit for coherent beam combination?
So first of all, what we've seen actually during the amplification process, we can see that we have a good mixing of the pump, of the incoming pump light between the different cores. And that means that also, even if the excitation is not completely homogeneous, at the end it becomes more and more homogeneous once you extract more from the different cores. So this saturation effect basically helps you. So this looked quite well from this kind of view. So what was the second question again? Sorry.
Yeah, basically, I mean, if there is
yes, the question is, does it impact the coherent combination process? And it depends. If you only go to the average power combination, then the coherent combination process is very forgiving for having different power levels in the different cores. You can calculate that, and even if you have a lot of difference, use the same combination elements, it doesn't really matter. The only issue that you might have is if you have work in a regime that you have a certain amount of non-linearity in the different cores. So example, the cell-phase modulation. If we go in most systems, we work at a certain level of cell-phase modulation. It's still quite low, so it doesn't impact the pulse quality too much, but it's still there. And if you have difference between the different cores, this can impact your combination more than this intensity. The intensity is not the problem, or the power level itself, but basically the phase. This is always the case with the coherent combination process, spatially and temporally. Difference in intensity are not the issue, different in phase are normally the issue. But even here, this kind of saturation effect helps you a bit in the different cores, that it converges against a certain amount of output power. So from this point, you have to take care of that, but it's not, I think, not a deal breaker so far what we have seen. It's forgiving enough, the coherent combination process, that this is doable.
Okay, thanks. Further questions?
Okay, thank you. On one of the first slides, if I remember correctly, you showed that the pump wavelength of the 2 micron is below 1 micron, so 700 something nanometer. So the quantum efficiency is like below 50%. Is this right? And if yes, is this a problem?
It depends. Yes, you are right. I have to get back to the slide. So yes, that can be an issue if you go to 793, but you have to see where we are. So here. Yeah, so it can be an issue. However, there are different like cross relaxation processes where you can actually use you can go to a different state. So the scheme of thulium is quite complicated. There are a lot of different energy levels, and depending on how the composition is of your active material, it's possible that you can get 2 photons out at 2 micron for 1 photon at your pump wavelength. They have certain cross-relaxation processes. And if you go to this regime, you can get to quite high slope efficiencies also of, let's say, 70% or so. If you get to this regime, yes, of course, if you do not work in this regime, you are at a lower slope efficiency than compared to ytterbium. Yes, this you have to take into account.
Thank you. You showed in your last slide that you achieved 37 millijoules out of the fiber.
Yes.
So dividing by 16 cores, you're at 2 millijoules per core.
Yeah,
right? It seems to me very high since the course is
yeah.
small.
So this was amplification of nanosecond pulses, also a bit longer than CPA. Maybe I didn't mention it. It was about 20 nanoseconds. Normally, you can stretch up to, let's say, 5 or 10 nanoseconds. This was a larger stretched pulse duration. And here at this point, you also do not care about nonlinear effects. This was just for extraction of nanosecond pulses. Okay. But you're right, this is a bit more than you would normally, but not much more than you can do in a CPA regime, where I've said you can do multiple 100 microjoules depending on your stretching factor, maybe to a millijoule. So it's a bit more, but also a bit longer pulse duration because these were directly nanosecond pulses.
But you achieve typically 1 millijoule per core.
Yeah. This is something I would say with large pitch fiber. If you have a sufficiently large stretcher, this is about. Okay. Depending on your fiber, exact fiber, the diameter of your core, but this is rough value. What's achievable, I would say.
Okay. Thank you for this nice talk. Concerning the applications, you mentioned that 2 micron was better wavelength than 1 micron for high harmonic generation.
Yes, sometimes.
Does this mean that 2 micron is some kind of optimal, or should we go even beyond this wavelength
so
range?
It really depends what you want to do. Normally, the issue is of high harmonic generation. If you go to lower wavelengths, if you go to 500 nanometers or so, you get a very high efficiency of your HHG process. But you cannot go that far in your. It's a bit normally it's not intuitive if you're not working in this field that you start with a longer wavelength and get to a shorter wavelength. But what I'm always told is because your optical cycle is longer, you can accelerate your electrons that you extract basically in this high harmonic generation further. They're longer and they get more energy. So the optimum always depends where you want to go. So normally I think they always try to go to a wavelength where they can reach the energy of those XUV photons they need, but also not longer to do that. But I know there are developments to go even further than this water window, which is about 200 electron volts or 300 electron volts. If you go to kilo electron volts, there are works on that. They try to go to this mid-IR regime of a few micrometers. Yes, but it always depends where you want to go. And there are always benefits and drawbacks in this process. So there's no optimum. There's, I think, only optimum if you know what you're doing. You want to have this wavelength regime, then you can see which fiber or which wavelengths you want at the beginning. And if this is even possible, if you can go there.
All right. Thank you.
Okay. Any questions from the web? So there's nothing in the chat. If not, then let's thank Arno once again. So we'll move forward to the next presentation. Will be given by Christian Vogtländer from FBGS Technologies. He will report on high-strength fiber Bragg ratings for sensor applications. And Christian actually made his PhD a couple of years back in my group, inscribing Bragg ratings into fibers, and he's now still continuing this in his professional life in a company. So he's the R&D manager of FPGS technologies since 2015. Yeah, and especially focusing on optical sensors.
Okay, yeah, thank you, Stefan, for the kind introduction. Yeah, in the next minutes, I will speak about high-range fiber break gratings for sensor applications. Yeah, my name is Christian Vogtländer, and I'm from the company FPGS. FPGS is a Belgium, German-based developer and manufacturer of high-range fiber break gratings, interrogators, sensors, and fiber optic sensing solutions. Our company mission is basically to become, through unique manufacturing technologies and application know-how, the worldwide market leader for tailored fiber optic sensing components and selector fiber optic solutions. Yeah, our company our headquarters is located in Jena in Germany. That's also where I'm working. There's the production of the gratings of our draw tower technology and femtosecond technology, as well as the development around special fibers and fiber break gratings. In our second location in Belgium, we have our sales and department, and also the development and the assembly of measurement system, the so-called interrogators to measure the fiber optic sensors. And we also have do R&D work around the application engineering. And then as well, we have an office in China for doing sales and application of the sensors. In the next part, I will explain a bit the grading principle and how we use these fiber gratings for doing sensing. Yeah, as you know, we use a fiber, typically single mode fibers with a core in the middle, then cladding surrounded by that, and the fiber usually also has a coating which protects the fiber. A fiber optic a sensor, or the so-called fiber break grating, that is a permanent periodic refractive index change of the core of the fiber. Such typical sensors have, or fiber gratings for sensing, have lengths in the range of millimeters, so 1 millimeter to up to 10 millimeter. And as the grating itself is not really visible after the production, we also mark the fibers that we and also later on customers can find the gratings back. What happens now if we illuminate the grating with light, if we couple a broadband light source into the fiber, then only a small narrow part is reflected by the grating, while most of the transmitted light passes the grating. So, and which wavelengths reflected is defined by the Bragg condition, which is 2 times. That's good. Okay, the reflection is defined by the Bragg condition, which is 2 times the refractive index of the guided mode times the period of the grating. Now, what happens if we use the FPG as a sensor? We can use it and strain on the fiber. And then what will happen, the period of the grating will change. And with that, the reflection wavelengths will shift to a higher wavelengths. The advantage of using Bragg gratings for sensing is that we, compared to normal electrical sensors, we can put many gratings behind each other in a fiber. That's so-called multiplexing technology. There are different ways. One is to use the WDM technique, wavelength division multiplexing, where each grading has a different period and reflects the light at a different wavelengths. And if we do now, for example, temperature sensing and use a localized heat source, we can see that if we move along the fiber, the response of each grading can shift, and with the fast response of the gradings, also quite good time resolving can be done. The number of gradings in such a fiber is mainly limited by the measurement device, and here, for example, this is a spectrum where there are 70 sensors in one fiber between the wavelengths of 1570 and 1610 nanometer. That means by this multiplexing technology, we are capable of putting quite a lot of sensing point into a fiber. The next part, I will describe our technology to produce such gradings. And there we have two technologies. One is the DTG or draw tower technology, and one is the femtosecond technology. First, I will briefly speak about the draw tower technology. As the name says, we use a draw tower and draw the fiber. Basically, we start from a preform heated up to 2000 degrees Celsius till the glass melts, and then we draw the fiber. Directly after the drawing, the gradings will be inscribed by an interferometric technique into the already cold fiber. After the inscription, the fiber is moved to the next position where the coating is applied on the fiber. That means at that technology, we are capable of writing the grading before the primary coating is done on the fiber. That gives the advantage that there is no stripping of the coating required to write any grading. And this is done in the process before. After the coating is applied, it will be cured. Then the grading position will be marked, and then with that highly automated process, it is possible to write in one fiber piece several hundreds, even up to several hundred of thousands of gradings. The second method I will talk a bit more in detail is using femtosecond laser to write the fiber bulk gradings inside. And here we use the nonlinear absorption process in the focus of the femtosecond laser. That means the local refractive index is changed in the transparent material. The good thing on that technology is that we don't need any photosensitivity of the fiber core. So that means it is independent of the type of fiber. It can be standard germanium doped fibers used, which are photosensitive, but also pure silica core fibers, which have no photosensitivity. Another difference to using UV techniques that the femtosecond modifications have a much higher thermal stability. And also a good thing is if you use a laser, which where the polymer jacket of the fiber is transparent, we can write through the coating of the fiber. That means with that technology, we are capable of taking any already produced fiber and write in a second step the grading at the desired positions. The method how we do that is the face mask technology. That means the grading period is generated by a face mask where the broad laser beam is diffracted into the +1st and -1st diffraction order. And in the overlapping pattern, there's a periodic interference pattern generated, which is then focused by a cylindrical lens into the core of the fiber. The advantage is here that we use a face mask made of fused silica, and the process itself is quite high reproducible. So if you write the same grading several hundred times, we get the same period because this is defined by the face mask. By focusing, we get a small localized FBG, and by fixing the face mask and the fiber together and moving under the laser beam, it is possible to scan across the fiber and also along the fiber. This gives the advantage of shaping the grading lengths and also the profile of the grading. So these two techniques, as I said, on one hand is the draw tower technique, and on the other side, the femtosecond technology, are capable of writing gradings, one before the coating is applied and the second one through the coating. And that means by using these, we get gradings with quite high mechanical stability. So if we compare these to a pristine fiber, so basically if we do destructive pulling tests on fiber, we see that pristine fiber has a tensile breaking strain of about 7%. And if you compare that with fibers with DTGs and FSGs inscribed, there is no significant difference. So the mechanical stability of the sensors are really high. And if you compare that to standard strip and recoat gradings, where we have usually breaking stability of just 1%, this shows that these two techniques are capable of writing really high mechanical stable gradings. In the last part of the talk, I will speak a bit about applications where these sensors will be used. And the first one is pipeline monitoring. And here, especially using enhanced distributed acoustic sensing. That's now then what is distributed acoustic sensing? A DAS system detects vibration in fibers like acoustic changes along the fiber. And one can imagine that that works like a small microphone in the fiber, that are at each position, there are small microphones along the fiber which detect acoustic changes. The systems are based on OTDR technology, based on optical time domain reflectometry. The return signal usually is analyzed in the frequency and also in the amplitude. The good thing about DAS systems is that they have really small resolutions. They can pick up strain, so changes in the fiber in the range of femto or picostrain. On the other side, it is hard for these systems to evaluate absolute changes. So usually this is just a relative change what they can measure. How does the operating principle is? Usually this is based on coherent optical time domain reflectometry. So that means a coherent laser pulse is coupled into the fiber, and then the scattered light, which is scattered by the fiber itself, is then detected. The acoustic disturbance along the lengths have small elongations and compressions, and these are usually picked up. When we look now to such a signal, on the bottom there's a graph over the fiber lengths of a standard single mode fiber, which is typically used for that fiber. So there's normally no gradings inside. That's standard fiber of 22 kilometer. One can see that the signal drops, and at the end we have really low low signal and higher noise. If we bring a fiber at the end, which has an increased Rayleigh backscatter, that's the green part where you can see you can increase the signal. And this principle can be also used by using gratings. If we write gratings with a very low reflection in the fiber, these are doing the same. They just increase the reflection. Also, we don't have the scattering effect. We have direct reflection back to the source. For this method, usually not the different periods were inscribed. Usually, all gratings have the same wavelengths, and depending on the system and application, the bandwidth will be usually tuned. But usually the bandwidth on the range of 1 nanometer up to 25 nanometer, depending on the bandwidth of the source. And also on the measurement device, the reflectivity needs to be adjusted. That means for each system, the reflectivity needs to be addressed to the right. So reflectivities are in the range of 10 to the power of -5 up to about 1% per grating. And this can be done by tuning the inscription parameters during that inscription process. That means also for writing these grading sensor dots in the fiber, the distances can range from centimeters up to meters, and that's also depending on the application. So typically these gratings, what this also required for the grating, that they have no additional or no high loss. That means if I have several hundreds or thousands of gratings, it means each grating needs to have a low loss per grating. And that is also possible with the both technologies we have. And the good thing, these enhanced backscatter fibers can also work in quite broad temperature range from -200 degrees up to 300 degrees Celsius, which is possible. And as we use these two technologies, we have a high mechanical stability. This is especially for the handling process important, because usually the fiber are in the field, not directly where they are. They need to undergo a kind of cabling process. They need to get additional protections. And during that, if you would use strip record gratings, the probability of fiber breakages are quite high. Okay, this was for the application around enhanced backscatter fibers. Another application for using gratings is, for example, in aerospace applications, where the sensors can be used to monitor changes in parts, especially as there a lot of composite materials are used. On the left-hand side, you can see, for example, the deflection of the wings of an unmanned drone, where there several sensors were integrated into the wing. And also in other composite parts, there are grating sensors used to check the mechanical integrity of the components. As well for temperature system, like in overheat detection system. Another different application I will come as the last one is using fiber grating sensors in medicine. And this is also a quite interesting part, as there are more and more procedures gonna take minimally invasive. So that means the the surgeon needs to know where he's doing and what he's doing inside of the body. So, and there are a lot of challenges for minimal invasive procedures. Usually to see where catheters or needles are inside the bodies. There are a lot of techniques used at the moment, like CT or X-ray, to check that. And the idea is to overcome this and use fiber optics without having that technologies. And also for working on robotics, there's the same procedure. Then if the doctor is doing a surgery with the robotics, he needs basically a feedback from the robot. Is he putting too much force on a tissue or not? So that's called force feedback, which also is necessary in medical applications. So, and there's that means there's a really high demand on tracking forces and also position and navigation systems in the medical purposes. For this, we have different different techniques. One is based on navigation, and here there we use not a single mode fiber, there we use multi-mode fiber to get to build up three-dimensional navigation systems. Okay, this is was a brief outlook as for this application, and here I thank you for your attention.
Thanks very much, Christian. Other questions? So I've one. How do you differentiate between strain and temperature?
Yeah, that is not easy possible for the grading, because the grading itself just or what we see in the end is just a wavelength change, and we cannot differentiate from that if you have that. So that's why usually it is common to have, if in the application it is known that both can happen, that there's a kind of a reference grading. For example, if you know we have strain and temperature, we have a reference grading, which is built in a strain-free environment where we make sure that there is no strain, and we can measure with that the temperature and compensate for that. Mm-hmm. That is the most common technique for doing that. There are also other ways of using special gradings where one can measure both methods at the same time. But these are also then limited a bit in accuracy.
Okay, thanks. So we have one question here from Alain.
Yes, hello.
Yep, we can hear you.
Yes, thank you for this interesting talk. I have just one question, please. Do you make fiber grading on PM fibers, for example, polarizing maintaining fiber?
Yes, that we also have done. We also have produced gradings in PM fiber. Yeah.
Okay, you're using probably the femtosecond laser writing technique or the UV?
We have used both techniques so far. So, for the draw tower technology, we basically need a preform to do that, and with the femtosecond technology, that is also possible by having later direct the fiber and writing the gradings inside. That's
okay. Okay, thank you.
Okay. Further questions? So if this is not the case, thank Christian once again. So when we move on, the next presentation will be given by Thorsten Göbel. So he's a PhD student in my group. He's also working on fiber Bragg ratings, but with a different focus. So formerly he was also working on sensing applications, but now switched a little bit topic and moving to selective light filtering. And he was also enrolled in a Max Planck Research School at Erlangen, or a joint school actually between Erlangen and Jena. And today he will be talking about fiber Bragg ratings as multi-notch spectral filter components.
Yeah, thank you very much for the introduction. Yeah, so as I'm going to talk about multi-notch filters, I want to first introduce or motivate my talk a little bit by the application, which will be the OH emission inside the Earth's upper atmosphere. And for this, I want to show you a short video. And what you can see here, the bright dots, these are the stars. So this is a video of the night sky, but recorded in the near infrared. Then there are some black dots, which is dirt basically on the sensor. And then you have this what looks like clouds, but this actually is an emission in the Earth's upper atmosphere. And what you can see now is like how this is moving on the time scale of minutes. So you see these stars moving due to the rotation of the Earth. And then you see the clouds moving over the sky. And because these emission lines are like kind of magnitudes higher or more intense than the faint background of stars and galaxies, this can quite drastically disturb the observation in the near infrared. And also because the time scale is more on minutes, it makes it very difficult to take any kind of reference measurements, as the situation may have changed during that time. But there are some properties of these emission lines, and so this is that this is how the emission lines look like. They are spanning quite the near infrared, starting around 800 nanometer, but having their peaks at the 1500 to 1600 nanometer area. And so now the question is, what can we do with it? This in the first place looks like it's really disturbing us, but actually if we have a closer look into these lines, they are very narrow, so they can have bandwidths in the range of 10 picometer. So which means they have quite a lot of space in between where we could see through when we just get rid of these lines. And so this is now the question, how can we get rid of it? And here we come to the place of fiber Bragg ratings. So as introduced before, fiber Bragg ratings are a periodic refractive index change inside the fiber core. And the reflected wavelength is based on the Bragg equation. So this is what you can see here. If we shine in with white light, then we get, for example, a green light back, which is based on our Bragg equation. So mainly on the period of our grating. And this will produce as a reflection spectrum. However, when we reflect light, this is obviously missing in transmission. And so this is what we are utilizing now for our gratings as transmission filters. Another very important property what we have to say is that these FPGs can only work sufficient in a single mode regime, otherwise the resonances will occur at different wavelengths. And so if we place now these resonances on top of our OH lines, then we should be capable of filtering these out. And so here is an example given how this situation could look like. So we have our night sky, and we use a ground-based telescope. Typically we couple into multi-mode fibers, because here we have a very large core, and it makes a very high in-coupling efficiency. And so as I've said before, we need to go to single-mode fibers. So there is this device which is called photonic lantern, and this couples our multi-mode light into single-mode fibers. And now inside of these single-mode fibers, we can implement our fiber Bragg rating filters. Later on, we can also recombine them back into a multi-mode fiber and send them into our spectrograph for spectral analysis. And by this, we can, in principle, suppress the OH lines while still having enough light in between passing through for spectral analysis. And next, I want to discuss a bit about an example. So we could, excuse me, this is the wrong slide. So first, the question is now, how can we realize the structuring? So we heard in the talk before, when we want to use an ultra-short laser pulse, that we have a nonlinear absorption process. And I want to describe this a bit more in detail. So what we have is, in the first step, we have a multi-photon absorption occurring, and once enough electrons are coming up into the valence band, into the conduction band, then we can have a further absorption, and if these electrons get enough energy, they can have an avalanche ionization process, and both together will deposit energy into our focal region. And now, a bit depending on our energy regime, we have different effects occurring. So one effect is that when we are in a low energy regime, we have a constant or homogeneous refractive index change. So this is basically an effect by melting and densification due to the rapid cooling afterwards. In a second energy regime, we get a formation of so-called nanogratings, and due to this grating structure, this will cause an anisotropic refractive index change. And finally, if we use too much power, then we would end up with small voids inside the volume. However, this is not what we want to do, because in particular, the void regime is a regime where we cause loss due to scattering. So we are focusing on this low energy regime. So this is how we structure our transparent material. But how can we get the period inside? And then we come here again to the phase mask technique. So as Christian Vogtländer explained before, we use a phase mask which diffracts our light into the plus-minus first diffraction order. And here I want to highlight a bit then how this looks like. So we have an interference pattern underneath the phase mask, which exactly is half the phase mask period. So, and this pattern then gets imprinted with a cylindrical lens into our fiber. But one thing you can directly see here, this limitates our flexibility. We want to address several different resonance wavelengths. We need every time a new phase mask. So this is already one drawback of this technique, that we are not flexible at all. However, we can increase the structure size when we move the phase mask and fiber together around. And this is at least the benefit of this technique, is that it is a highly stable process and it's very reproducible. So, and how could now such a filter device look like? We would use this technique to inscribe different gratings into our fiber. Just one example, if we take a fiber and we have now different positions, our gratings, then we could, for example, inscribe 10 gratings in such a fiber. And here is such a spectrum, how it could look like with 10 resonances. We can, if we have the right set of phase masks available, we can have we can address our wavelengths. However, as we have now 10 individual gratings, this gets a bit interesting in stabilizing these, because as you have heard in the talk before, they are very sensitive to strain or temperature changes. So you need to stabilize, if you want to use them as a filter device, you need to stabilize the wavelengths, otherwise they would move around and don't filter our light. So if we have 10 resonances, we need somehow 10 packages to make everything more stable. So this limits a bit the capability of inscribing individual gratings into the fiber. And also it makes it quite large, because this is what I want to show you next. This is the refractive index change in our fiber core. So if we inscribe, for example, 2 gratings right behind each other, we would require somehow a length of, let's assume, 50 millimeter here. So if we go now to 10 gratings, we would need like 5 times. So 250 millimeter. And this is already quite a long area just for 10 gratings. So, but what you can see is, so typically our refractive index change can be much larger than the 2 × 10⁻⁴, what I've shown here. Yeah, so there is still room to inscribe more structure on top of each other. So why not maybe just stack the grating on top? Yeah, so we shift now the grating on top of it, and not only one, we take more than this. And so as more as we stack these gratings together, you can assume that what you can see on the top part is the period distribution. This is now just a sketch, but what you can see, if we add now all these gratings together, this gets a very irregular pattern. And this is why we call this type of fiber break grating an aperiodic fiber break grating, because the period distribution is no longer periodic at all. It follows a somehow random pattern, depending on the overlap of these different periods. And not only the period is now changing, also the envelope of our refractive index structure. And this is a kind of interference effect, what we see here. So this is really the refractive index envelope. Is like the period we inscribe is around about 500 nanometer. And what we are seeing here is 50 millimeter. So this is the envelope we need to realize inside of our fiber core. And so you see this is getting very complex, and it's a very challenging task to inscribe such fiber break gratings with a very flexible period adaptation and at the same time a very flexible envelope change. And yeah, so the design I've shown here is basically based on a spectrum consisting of 10 resonances. And this is like how the initial design spectrum looks like. And we not just purely overlap our gratings, but there is a numerical tool based on the layer peeling algorithm, which calculates our profile and period distribution. And so when we take the given spectrum, we get the grating envelope as shown before, and the following period distribution. And what you can see here is we have a basic period of 535 nanometer, and then a large variation around which does not show any periodicity at all. There are also several phase jumps, what you can see in the top part, or somewhere where periods are falling very close to each other. So let's have a look into a magnification. So you can see that there is like no regular pattern at all. And it's like very challenging to realize this structure. But luckily there is one technique, the so-called line-by-line technique, which gives us the advantage of being very flexible. And so we use the femtosecond focusing with the objective and focus our laser beam into our fiber core. And now what we are doing is like with drawing with a pen, we can adapt the period very flexible by moving the fiber underneath the laser beam in a rectangular pattern. This gives us the flexibility of completely freely choosing the period. But not only this, the amount of refractive index change we induce depends on the speed we are moving across the fiber core. And so what we can do is we can also adapt the speed for every layer according to the refractive index change we want to address. And when we do both together, we can realize the aperiodic fiber break grating inside our fibers. Next, I want to show you a first result. So here's the transmission spectrum of a aperiodic fiber break grating consisting of 10 resonances. The green dotted lines you can see was the target wavelength, and the blue line is the measurement. And what you can see is basically we are matching our resonance wavelengths very well. Also, the suppression factor is exceeded most of the time, only for resonance at 1545, the resonance is slightly weaker. Additionally, what you can see, we have this kind of underground around our resonances. Some part of this is due to coupling into cladding modes. So because we make a very localized structure in our fiber core, the light is partially coupled from the fiber core into the cladding of the fiber, and so it's lost in transmission. But not all of these peaks correlates to cladding mode coupling. So what we did is we analyzed the grating structure a bit further by a simulation called rigorous coupled wave analysis. And if we do so, we see here now with the red dotted line that we get also from the simulation intermediate peaks, not only the 10 resonances we want to have, but also some in between. So I want to show you a small magnification from some particular examples. So you can see here that we have our addressed line with the dotted green line. And next to this, we see another resonance occurring. And so this is like, because the structure gets very complex, it can show even additional resonances. And we can predict them quite well with our simulation tool. Also, another thing what occurred here at 1553.5 nanometer is a resonance which was not intended. And this is actually the basic period which we used, the 535 nanometer, and it causes a kind of parasitic resonance. So we use this base period, and then it's modulated to address the resonance pattern. And for this initial design with the 10 resonances, this was not taken into account accordingly. But for the next design, we took this one and placed it also on top of one of the resonances so we can utilize it. And so, as I've shown before, we had a grating with 50 millimeter length and 10 resonances. And just to demonstrate that this is very nicely scalable, we just doubled the resonances to 20 and keeping the length the same. Of course, then we need to increase the amount of refractive index change we need to induce. And this leads to kind of weaker resonances because we are already in the saturation regime of our material. But nevertheless, you can see that we could address all 20 resonances. However, now the suppression factor is not as high as before. So there might be some room of improvement by making it slightly longer and also maybe improving the stability of the system a bit. Also here, we can match the simulation and it predicts also most of the resonances quite accurately. And so with this, I like to conclude my talk. So basically for achieving multi-notch filters, we can have either an array of fiber break ratings written right after each other into our fiber. This is a very stable and reproducible process, but comes with the expense of having large areas of structured fiber, which might need to be stabilized if you are working in a non-stable environment. So this can be overcome by inscribing complex grating structures and by the line-by-line technique, which is a very flexible tool to address these structures. And with this, we could inscribe resonances with 10 and 20 notches. And with this, I'd like to thank you for your attention and welcome your questions.
Any questions?
So can you comment on the, I would guess for the second type of grating, you need a lot longer production time, right?
Mm-hmm.
How long does it take?
It takes currently around 15 hours for one grating.
Okay. And the standard one is?
The standard one with the face mask technique is rather fast, so you need like 5 minutes, maybe 10 if you make a very long one.
Okay, Alain?
Yes, it's me again. Hello, thank you for this talk. I have several questions, please. If you go back to the when you showed the profile of the refractive index change, I assume this was simulated, not measured. you know, for when you showed, yeah, exactly.
Yes, this is a simulation, yes.
Okay, so it's not measured. Okay, and also at some point when you saw the next step, you show the transmission depths. If you go to the next slide, I think also continue. When you did the line by line, yep. If you continue, please, is when you have the transmission depth. Exactly. So here you have around 40 dB of transmission depths and like very good transmission depths. So how much was the length of this grating?
This was 50 millimeter. So the one I've shown you before.
50.
Yeah.
Exactly. And line by line, you were assuming lighting periodicity, you said, of, so it's first order grating mostly.
Yes, exactly. It's
So
based on the first order, yeah.
No, so using probably a green laser and doing line by line with all objectives.
Yeah, so we're using the femtosecond laser and the
Yep.
line by line technique to address.
Okay. And then you mentioned about increasing the refractive index change. And does this cause problems in inducing more coupling modes, cladding modes? Sorry.
Yeah, so this is like because our focal length is not long enough to cover the whole core. We get a slight coupling, and this is what you can see here in between. For example, here this comp is probably a
exactly
coupling. And then, yeah, so because the structure becomes quite complex, also the coupling into cladding mode becomes a bit more complex. But yes, several of these intermediate peaks can be correlated to cladding mode coupling.
And when you write the similar gratings, you write them all on the same plane, or you shift the plane a little bit, or not? You know, there's that focusing because you're not covering the whole core. Maybe you write one core, the first one at, let's say, the first grating at 1520 at one plane. Then you move 1 micrometer down and then write another grating, or all of them on the same plane?
No, this is actually really one grating. So this is, I get the numeric design, and based on this, I get one grating structure, and I inscribe this from the beginning to the end.
With different periodicities, like you mentioned earlier.
Yeah, exactly.
Okay, I see. Okay, thank you very much.
Okay. And then, I guess, thanks, Thorsten, once again. And now we'll actually switch from fibers to bulk material. And the next presentation will be given by Felix Dreiso from Schott Minifab in Jena. And he will talk about advanced laser-based glass structuring for microfluidic diagnostics. And Felix is a scientific advisor for laser and bonding technologies at Schott Minifab. And yeah, he's working on laser or ultrafast laser materials processing for quite some time at various positions. He was a PhD student in my group, and then did his postdoc here, and also with the Fraunhofer Institute. And he was also with Macquarie for some time in Sydney, and the Günter Köhler Institute for joining technology and materials testing in Jena. Okay.
Stefan, thank you for invitation. It's a pleasure for me to be here at my old institute. Yeah, we heard a few talks about fibers. Today, I want to show you what is possible in the meantime in industrial production with ultra-short pulse lasers. So my agenda is at first a short introduction to Schott Minifab, who we are, what we are doing, then basic ultra-short pulse laser absorption for materials processing. Thorsten already introduced the main concept. Then I show you what laser processes are possible for glass processing, and then some of our product specials, what we are selling every day. So Schott Minifab is a part of the Schott company, and yeah, Schott, you may already, all of you may know Schott. the most famous is the Ceran cooking field. So a lot of people have that in their house. Shot Minifab is just a small part of this big company. We're only 215 experts worldwide. What we are doing is we are using the glass and bring it to diagnostics for life science consumables, but also for the development at the institute. And our core market are diagnostics and life science. So wherever you have, for example, point of care diagnostics, you come somewhere, need a blood test, and there's a small chip in the blood test where the blood comes onto a glass, and then maybe the glass comes from us, just for an example. Second example I want to mention here is the next generation sequencing. It's DNA testing. When you go somewhere, want to test your DNA, you get a next generation sequencing DNA test, which is happening in a microfluidic chip. Yeah, this microfluidic chip needs a high accuracy, and therefore it's made of glass. And we're producing, for example, these so-called next generation sequencing chips for our customers. In Jena, Minifab is doing only the glass parts of the microfluidics and diagnostics. We get the raw glass even here from Jena for most of our products. Minifab is then processing the glass in gray room conditions. We're marking, patterning, have a quality control. Then it goes to cleaning. The main business, what we're doing is the coating. We bring a special coating on the glass that the biology sticks to the glass, and then we pack it and have a functional QC afterwards. You see down here a few of these glasses which we sell. Yeah, at first you see at the first picture that we can cut arbitrary shapes into the glass with several thicknesses which we can cut. In the center you see the markings and the patternings. So we have this black marking that you can nicely read. Currently we're switching to directly laser marking, which is then not black but white on the right hand side. And we have this pre-scoring technology. So if you have small chips in diagnostics, the chips are maybe 3 millimeters to 10 millimeters. If you want to sell them, you have to sell them in tiny parts, and the customer want to make on every tiny part a certain application. It's really a mess. So what we're doing, we sell a wafer. The wafer is already pre-scored. The wafer is easy to package, and the customer gets a large sheet, and they can maybe on this. It's shown roughly 10 by 10 chips, but we have also a 30 by 30, means 1,000 chips on a wafer, and the customer can make process the whole wafer. And just before it comes, the chip goes to the test, it's singulated, and then the single chip is placed on the wafer. And we're also making 3D structures for the microfluidics. Yeah, before I continue with the laser processes, I would like to tell you a small or a short story how SCHOTT came to the ultra-short pulse technology. Recently, I met a guy who started this business, and he said, "Oh, it's now 12 years ago when we started the ultra-short pulse business," and I was saying, "Oh, it was my PhD time." When SCHOTT already started glass cutting. Yeah, and during my PhD time, I think, Stefan, no one was really discussing about glass cutting. Yeah, it was a lot of processes, hole drilling for automobile industry. And I can remember it was 2014, 15, when you heard of on the conferences about glass cutting. It was times of iPhone 4, where you had the push button, where you had to cut out the glass for the push button on the iPhone 4. During that time, it came up in the industry or in the laser companies to cut the glass. But during that time, Schott already had the laser machine there and was developing the laser processes, and it was the end of this or the shutdown of the solar business at Schott. And they came to the solar plant and found ultra-short pulse laser machine standing there in the last part of the production hall, and no one used it. It was completely new, unused, and they said, okay, we take it to our central R&D. And then they had the machine there, and yeah, and no one was really aware of what doing with ultra-short laser pulses in the Schott company at Zone Glass. And it took really a while to find out what they can do. And during that time, they started already to develop glass cutting. At first with ablation, making curves, breaking it. And in the meantime, we have this machine, similar machine in production. And it took really a quite long time to bring this process to stable industrial production. But with this story, I want to continue my talk. So laser materials processing is simple metals. You have an absorption. Yeah, you shine with the laser on it, and you absorb the laser energy, and you process your metal. In glass, it's really difficult. Yeah, look through the window. Window has no absorption. How can you process your glass? Yeah, it's really a good question. Yeah, in metals you have free electrons. So free electrons are absorbing, and you don't have them in glass. It's an insulator. You have no free electrons. But how can you change this? Yeah, Thorsten already said you bring some electrons to the conduction band by multiphoton processes. In principle, it's a simple answer. You make your glass intransparent. Yeah, then it behaves more or less like a metal. You have free electrons, and the free electrons can absorb the laser energy, and you have this so-called avalanche ionization, which we have seen before. So very simple story. I think this process can be very complex if you look on it in detail, but I want to today just show you the processes which you can do with ultra-short laser pulses. So ultra-short laser pulse processing of glass, you have basically a few processes. At first, you have the standard ablation on the surface, which you have also metals. Glass is transparent. You can focus also your laser beam on the backside. So you can make a backside ablation. You can focus it in volume, like we have seen for the fibers, for example. And we have this last process for filamentation, which is a mix of all this. You focus in the volume, but your modification typically extends from bottom to surface in a tiny area. Let's first start with the ablation. Ablation, you make some profiles in there with certain functionalities, certain properties, depth. We have a limitation of the wall angle. So the wall angles typically in the order of 80 degrees. We have achieved very high ablation rates in the order up to 30 cubic millimeters per minute. And there you can do quite a strong material removal. What we use in daily life is
Sorry, can you hear us? Excuse me, we lost the sound like 1 minute ago. Everybody is not able to hear anything. So, okay, expect, not from me anyway, but it sounds like expect.
Hello? So does it work now?
Stefan?
Yes? Does it work?
Yes, now it is working.
Okay. No, I guess we have to use the other microphone. And I try to fix that one. Oh. Okay. Does it work? Yeah. Okay. Okay, maybe I start again with that slide. So what we're interested in is a marking of our glass. So Borofloat has a top side and a bottom side due to the floating process. The bottom side lies during the fabrication on tin. And so it has a residual part of tin on the bottom side. So we have a bottom and a top side on the glass. And when we want to process the glass, we finally need to know. And therefore we use the so-called F mark. Is it still working? Hello?
We lost the image, but we have the sound.
You can't have everything.
But we still see the content. We can still see the presentation. Now it's back.
That's back. Okay, F mark to mark the front side of the borrow plot. And you do not want to disturb the application, so you want to have this F mark almost invisible unless you want to know it. So what you're doing, what you need is clean and virgin surface, the F mark almost invisible. If you need to know where it is and have an appropriate lighting condition, then you want to see it. And what you're doing, you focus below the surface with a certain focusing condition, and you bring your F mark into your glass slide. Of course, you see it here now in this image very brightly, because I want to see it and show it to you. If I put this glass slide on just on daylight, you won't see this F. So applications are for us, of course, the front side marking, but it's also used for genuineness. So if you have precious crystals or precious whatever, you just make an ID code into it, and you can it's safe for reproduction, and we have no visual distortion for most applications. In-volume markings. Okay. In volume, what you also can do is weld the glass. So, for example, if you want to join two glass plates here and encapsulate a certain component, you bring the glass plates together, focus the light beam into the interface between two glass plates, and this is the way that the glass melts in the. You still hear me?
Yes, we can still hear you.
Okay. You focus the laser beam into the interface and weld the glass of your glass component stays cold, but you weld it in a very localized position, and so you protect your components or your delicate parts of your later device. And how does it work? You just have several wafers, stack them together, weld it with our so-called primo-sailor laser technology, and finally you dice it to your desired size. And dicing you can also do with the laser, with the so-called filamentation process. Filamentation, I don't like this word, but everyone knows a filament is a tiny area, and everyone uses it in daily life. So yeah, I have to do this as well. Yeah, it's describing the cutting process. So you describe your glass and breaking process. So you describe your glass and break it afterwards. We do this with a picosecond laser, the speed of roughly 1 meter per second. You see here the high precision glass edge, no distortions. Separation can be done by manual breaking. For example, thermal cleaving with a CO2 laser. Strengthened glass is self-cleaving, so it breaks by itself. The edge is perfectly 90 degrees. We have a roughness of in the order of 1 micron. You see it at the bottom. The laser cut edge is slightly frosted. The precision is given by the machine technology in order of 20 microns, but 20 microns on a meter scale. And it's almost free of particles. So you see the image here is directly taken after the cutting process in the production hall. So the particle load is quite low. Yeah. Yeah. Okay, so if you look at it in detail, the laser process is on the left-hand side. You do several shoots quite next to each other in the glass.
And what happens, what you see there is there's a crack propagating from dot to dot. I think Malte will give a next talk a more precise insight how these cracks propagate, how you can control these cracks. And due to these cracks from shot to shot, you can do then the breaking process afterwards. Cutting is a simple example, but you can cutting is a simple example, but we can also do very with arbitrary shapes. We call this flexinity. Flexinity due to the nice flexibility. Yeah, with applications in various fields, biotechnology, semiconductor industry, sensors, MEMS, whatever. It works in all of our shot flat glasses, can be ultra thin, you have high chemical resistance and so on, what you have in the glasses. Some words on our products for the diagnostics is we typically use the glass not only for flat samples, but also for 3D structures. 3D structures are bonded. We start with a base layer. Most of our products are coated. The coated for bonding is still under development. Then we bring a so-called interposer as an intermediate layer. It's cut through here. And then we cover it with the top layer, where you have the SS ports for your fluidics. We bring this together and have a certain bonding process, can be the laser process, which I showed before, but also then a fusion process. And for example, here's the image on how it looks like later on with a porthole centered at the interposer edge. And it looks quite nice, as you can see here. We do this on a wafer scale. After that, we need to pre-score these chips. You see here these white lines on the chip, and these white lines is the second cut after the bonding, after the assembly. And we deliver this product, for example, to the customer, and the customer does then the breaking into his own chips. We can sell the large part, and the customer just can do the breaking. Some final product features. Yeah, we have this wafer. It's a real image of a demonstration product. We have this image, then we're doing the pre-scoring. It's only slightly visible on the image. Yeah, we're enhanced here the lines. And you can, for example, put some features on the chips to avoid rotation symmetry, bring some serial numbers on it with the processes we have, and also machine readable identifiers, data metrics codes, and so on. Yeah, to conclude the talk, we have versatile glass structuring methods in-house brought to production with Ultrashort laser passes, with several processes like surface inner and outer contour cutting, and also the so-called pre-scoring. And I showed you also the flexinity products for the advanced wafer level packaging. And I'd like to thank you for your attention.
Yeah, thanks very much, Felix. Other questions?
Yes.
Hey.
Okay. Okay. If not, I have for the people here, I have some glass to break. Yeah. With me, so it's a demonstration. You can just make small
Yeah.
pieces.
Maybe just one question from my side. I mean, for all the microfluidic applications, some people use plastics. You are using glass, so
yeah, plastics, glass. So the question is very simple. If plastic is sufficient, use plastics, it's cheaper. Yeah, glass, it's mandatory if you have these. Therefore, I mentioned the example of next generation sequencing. There are people that do, or they have numerical apertures of 1 to 1.4. There's the optical quality of plastics, even COC is not sufficient anymore. Glass has to be used if you have certain requirements on chemical resistivity, with some applications where the customer comes okay with a high pH basic and yeah, things acid and base aggression to the chip, also some solvents. So plastics not resistant to solvents, temperatures, and so on. But if you have a simple process like a droplet generator for water and oil, take plastic, it's fine. You see it for the Corona quick tests. They are all made of paper, so no one wants to use the glass. It's too expensive there. Yeah.
I don't know. Okay. I hope we still have sound. So, yeah. Any questions from the web? No. Okay. So thanks again, Felix. With this, we'll move to the final talk.
Sorry.
Maybe we can use the other microphone again. Ah. Somebody hear me? Okay. So is it working? Is it working? No.
Can you hear me?
Yes.
Okay, fine.
Perfect. So we have the other sound back. Okay, so for the final presentation, while the people here in the audience are breaking the glass chips and having a lot of fun, that's great. So we'll move on to Malte Kumka from Trumpf Laser GmbH. He will talk about inscribing modifications by tailored ultrashort pulse beam for glass separation. And Malte studied in Hanover and did his PhD in Berlin, and then worked at Detwiller for laser engraving systems and also for lasers for materials processing at Haas Laser. He was managing director of JTOE and starting the fiber laser activities of Trumpf and Jenoptik here in Jena in 2007. And now he's at Trumpf working on advancing industrial laser applications. Yeah, and with this, stage is yours, Malte.
Yeah, thank you very much for the introduction. So it's a pleasure for me to present the work on the technology for laser cutting here in this audience. So nearly 10 years ago, we started a cooperation with a group of Stefan Nolde on laser cutting, and we did some fundamental work on the ultra-fast interaction with the material and how to tailor. We started with some pump probe experiments and so on, but I do not want to step into this, but will focus on the technology this allowed to develop for industrial applications. So, and of course, this is a team working on this at TRUMPF on different locations. And just to give an impression. Wo ist die Maus? Da ist die Maus. Let us take the cursors. Okay, so laser cutting with transfer materials, so it's used in the industrial use, but it further develops. So the cutting by modification inscribed by elongated beams, by ultrashort pulses, relies on precisely controlling the do not seem okay the absorption and the dosing and so on, and meanwhile it allows by scaling the energy we can absorb in a single shot over the whole length. We can cut in a single pass architectural glass exceeding a thickness of 10 millimeters by using higher energy, but we can use it to cut through wires in glass from macro to nanoscale. We are able to cut thin glasses without problems in the breaking strength. This was a problem before. And this can be done by developing the technology for the optical systems and the beam shaping to allow even to couple elongated beams into curved surfaces. And it's a really fast process, Felix mentioned. So this is several meters per second inscribing speed for cutting in case you have really volume production by straight cuts. Let me go on. So first I want to go on with the elongated modifications for non-diffracting beams. This is very attractive because they do not change the intensity profile during propagation. And it's normally a two-step process. So first inscribing, and afterwards use mechanical or thermomechanical stress, or maybe chemical separation. So just to give an impression how this works. So this is inscribing. So 6 millimeters, then CO2 laser for crepe propagation. And then it's going to be easy to separate. Yeah, and not, and it's possible to generate complex shapes. Okay, we have these energy deposition by non-diffracting beams. The standard one is the Bessel-Gaussian beam, and it's diffraction free, as mentioned. It's self-healing, so in case you have a disturbance, it will heal out. Aspect ratios as high as 10,000 by 1 possible, and it's a simple and efficient generation of these beams. So by using hexagon, for example. So it has a natural resistance to spherical aberrations due to the conical shape, and the peak intensity ratio of the first to the surrounding ring to the center ball it's 1 to 17%. So it's very attractive, but you can generate other non-diffracting beams, and this may be useful. For comparison, you see the Gaussian beam on the left side. So typically for tight focusing, in order to generate the nonlinear absorption, then the length is in the range of 10 micron, and makes no sense for full thickness modification. But the Bessel-Gaussian beams, it has a circular symmetry, and often it's better to have an elliptical symmetry of the beam, or to split it in order, in principle, to generate in a single shot more lines, or to have it tilted in order to get beveled edges, or even accelerated. And everything can be done, and one has to find out what works for inscribing modifications suitable for separation. And we did a lot of work on this, and I can show a bit of it. So let us start with a face mask for the Gauss-Berton beam. So it's a conical phase distribution, and we have the phase marks on the left, the near field we use for inscribing, and this is the far field, how it looks like. And then we can cut out some segments, modify them, and see what happens. And you can see then, in case, for example, you shift the phase, have the same gradients, but shift the phase in these segments, you get elliptical surface, elliptical profiles, preferential direction, or you can make it even more complex. And there are lots of options you can carry out, and some of them are helpful, others not. Okay, so one thing especially helpful, this is the elliptical beam. So the optics on the left is an optic where you can rotate the profile, yes, within the optics. And by rotating this profile and inscribing the modifications, you see already cracks coming directly from the modification, and they are oriented in direction of the preferred direction of these elliptical profiles. And if you then put several of these beams in the picture below, in line, you see, in case the cracks are already aligned in the direction of the cutting of the contour, then they join and help separation. In case they're separated perpendicular, they do not join, and as you can see, this allows a huge distance between the modifications and joining the cracks far above the length of the initial cracks from a single modification. And this helps for several applications. As you can see, I have to do the next, otherwise the scale is missing. Okay, so on the scale on these view graphs is the modification distance. So the distance between two individual modifications. And then we have the separability. This means the force needed in order to separate later on. Felix, you have some samples with you, you can, okay. So the upper one is for 3.8 millimeter in thickness. And in order to separate them, 300 Newton are necessary for fundamental mode with a modification distance in range of 3 micron. And in case you increase it by far, you can't break, or it will not be directed by the modifications anymore. But by using an elliptical beam, you can separate them more and more, and you can then easily separate them. And this works for thin materials too. And then the appearance is different. So the modification itself normally are scattering. This is shiny, but in the cracks, this is reflecting. So the appearance is really different, and for some design guys, it's very important. And the other thing is that, of course, in case you can increase the distance, the feed rate can be increased. You get equivalent edge quality. The roughness is below 1 micron typically. And very often you can generate partly enhanced edge strengths by this preferential direction of these beam profiles. And then you see the 3-spot profile. And you see, okay, this seems not to have in these applications. You can see here, the beam profile here. These are 3 intensity maxima aligned in the contour, but these profiles inside, they are elliptical in the wrong direction. This is why it does not really help. Yeah. Okay, let's go on. Another thing is how to release inner contours. So the process is a zero gap cutting. It's how to release inner contours. And one way is to tilt the modification. And you can do. So you can do up to a certain extent. This, for example, is 80 degrees instead of 90 degrees, and this allows to release these inner contours out of the system. And for others, it's helpful for design reasons or someone. But in case you take a look how this is done, in case you have standard optics where the bezel axis is aligned to the optical axis of the system, then you see, okay, it's, let me see whether I can, there's, so it typically requires then a complicated 5-axis system, complicated control and so on. Yes. But it works up to a certain degree. So a specialized optics might help, where you can rotate the optics itself. But you enter in another problem. So the bezel-like beam, I mentioned it's not critical with respect to aberrations, but in case you tilt the beam, this causes deviation from the conical face shape. It has to be corrected. Otherwise, the disturbance will modulate in longitudinal direction. The profile will disturb the production, the profile. So the higher the tilt angle, the shorter the length of your profile if you don't compensate the aberrations. Okay, so it is possible to compensate, and it is possible to rotate the beam axis with respect to the optical axis of the system. But first, I want to step in another approach for generating even more complex shapes. And this is that you inscribe volume modifications from holographic dry beams, 3-dimensional beam splitters, so 3-dimensional multi-spot arrangements, and then use a second step for separation via chemical etching. So this is no longer a zero gap and helps a lot finer contours and more complex shapes. Okay, this is the correction of a curved surface. It's similar to what you do in case you have a tilt. So normally this curved entrance of the tube will disturb the beam, but you can pre-compensate by proper designing the optics in order to cut this. So this cut then is done by thermal load, so self-separating after CO2 laser treatment. But furthermore, you can do inner contours out of this tube, and these are released via chemical etching. So you inscribe a different modifications suitable for wet etching and not for separation by mechanical force. And you can do even more complex shapes with these multi-spot profiles. Very often it is used to increase the shock resistance of the glass. So to generate bevels that the break resistance is improved. And you can do other things. So some are designed, some are for mounting procedures. And yes, does this really work? Such a profile, you can see. Okay, how to design? Normally we do it. We are interested in a special modification, 3D modification in the substrate. We propagate backwards. So these are coherent beams. So in principle, you generate some hologram on this rear side, and there you make a diffractive optical element from, and this is used to generate the multi-spot profile. And then, for example, you can generate such profiles, and you can do this then by spatial light modulators or by diffractive optical elements. And then, yes, it really works. You can inscribe these modifications, and it works as we calculate. And what you have to take into account is that you have a huge volume of work, yeah, and that you have to ensure the tiny focusing over the whole volume. This requires really good design of an understanding of the beam splitter and of the system and how to generate these tiny spots in a single shot and not to move around. And in case you use a conventional spherical lens, you see the outer regions, the spot is disturbed, it will not initiate the nonlinear absorption, and it will not generate the gradients necessary for this cutting process, for these etching processes. But by designing then the microscopic optic systems properly, you can generate these tiny spots necessary for this modification process. Yes, and then you can inscribe the profiles. And this is really in a single pass, single side access. So no workpiece flipping necessary. And for these, the rotation of the profile is integrated into the system. So you can apply a simple three-axis system for inscribing even of these complex shapes. And yeah, different shapes are possible. And the designers are very interested in these shapes. But it's ongoing work on this, and we see large potential for other application, and all this based in principle on the fundamental work undertaken on understanding how how the interaction works, how to dose, how to localize the absorption. And I think we will see more of these applications, and are happy in case we can go on together. And for this, I would like to thank you for the audience.
Okay, thanks very much, Malte. Are there questions? So I have one question. You showed this chamfer in between. The first one, was that also etched, or before you started reporting about the holographic structuring?
Which one? No, these were mechanically separated.
Mm-hmm.
So in case the contour is not too complicated, this works. In case you do not have the zero gap, and in case the edge itself is not too complicated, which makes it hard to separate mechanically, because then in case you have sharp edges, these you detect very often then chipping by mechanical separation.
Mm-hmm. Okay. Are there further questions?
Yeah, thank you for this nice talk. So is it at the end you showed this quite complicated optic system, right? After the SLM, do you need to, can you do all your changes with the SLM only, or do you need to also optimize your optic system after that and design it specifically for the
I can say that for these complex shapes, so one thing is we normally apply the SLM for development purpose, to learn how it works and then how to design the different optical element. And for some of these shapes, the resolution achievable from the SLM is no longer suitable for the application. So we need a higher resolution than we can achieve with the SLM.
Okay, so if there are no further questions, then I would like to thank Malte and all the speakers once again. Yeah, with this, I guess we'll close the workshop for today. For me, it was really fascinating to see the different aspects, what is going on here in functionalizing glass or processing glass with ultra-short laser pulses, and also the development on the laser side. And the workshop continues in about a week, or next week actually, Tuesday the 24th in Portugal. And then it's about photonic materials for lighting. Okay, thanks very much.
Ja.